Let's get started. All right. Great pleasure to today to have Chris share his research over the past 6 years on atmospheric chemistry as it relates to ozone and mercury oxidation. Chris got his undergrad degree from University of California at Irvine, where among other things he worked with Eric Salzman on long-term time series and ice records. And so he came to see you with an interest in kind of work on long-term time series. And that's what he did. And today he's going to share us about mountaintop observations with sensors in the remote atmosphere.
All right, thanks for the introduction, Reiner. And thank you everyone for coming. So I'll just get started. So the title of my dissertation is, as you see on the slide, it's Mountaintop DOAS Observations of Trace Gases in the Remote Atmosphere, Relevance for Ozone and Mercury Oxidation. And so this photograph you see in the background here is a photo that I took at a remote high altitude mountaintop site in the Southern Hemisphere on a French governed island, Reunion Islands, between Mauritius and Madagascar. And this is one of the sites where we deployed our instruments, and you can see we're pretty high up above the cloud layer. And so here's an outline of my talk. First, I'm going to describe a little bit of an introduction to the atmospheric chemistry of stratospheric ozone and mercury chemistry in the atmosphere. Then I'm going to describe the methods that I used throughout this work, followed by a description of more than 5 years of long-term observations we made at these 3 mountaintop sites. And then I'm going to go into a description of 2 different case studies. One covering the observations of iodine and mercury over the central continental United States in Storm Peak Laboratory, Colorado. And the second from the Southern Hemisphere sites in Maido Observatory on Reunion Islands, where we observed a volcanic plume eruption from the Hunga Tonga volcanic eruption. And so first, some background. So why should we care about stratospheric ozone? So stratospheric ozone absorbs harmful ultraviolet radiation from the sun. And so what you see here is a graph of the solar radiation as a function of wavelength. The orange trace here indicates that what solar radiation looks like at the top of the atmosphere before it enters Earth's atmosphere. And the color trace here indicates what the solar radiation looks like at the bottom of the Earth's atmosphere, at the Earth's surface. And this red arrow shows where all of that ozone in the stratosphere primarily is absorbing ultraviolet radiation. And so ultraviolet radiation in humans can cause sunburns, skin cancer, eye disease, including cataracts, as well as suppresses the human immune system. It also causes extensive damage to aquatic organisms such as fish, amphibians, and plankton. And so how does ozone in the stratosphere form? So stratospheric ozone primarily forms through the photolysis of diatomic oxygen molecule. So when oxygen in the upper atmosphere is exposed to high energy radiation, it breaks apart and forms a single oxygen atom. And that single oxygen atom can react with another molecule of diatomic oxygen to produce ozone. And this chemistry was first sort of formulated in the 1930s. In the 1950s and 60s, it was discovered that hydrogen oxide radicals undergo these catalytic reaction cycles that can also efficiently destroy ozone, and these are referred to as HOX. In 1970, it was first proposed that nitrogen oxide radicals can also destroy stratospheric ozone very efficiently. Yeah. And in the following decades, it was discovered that various halogen oxide radicals, including chlorine, bromine, and iodine, also very efficiently destroy stratospheric ozone. And this is also in the context of where the stratospheric ozone hole was discovered. And so the chemistry that I'm showing here is a very simplified representation. In reality, all these chemical reactions are coupled and undergo interactions between these different ozone destruction cycles. And so, for example, the Brox and Clock cycles actually can interact with each other to further increase the ozone destruction potential. And additionally, both chlorine and bromine species can enter longer-lived reservoir species by reacting with nitrogen dioxide. So how will climate change affect stratospheric ozone? So climate change is predicted to increase convection, especially over the equator and in the tropics. And this is going to inject a lot of humidified air masses into the stratosphere and a lot of water vapor into the stratosphere. And all this water vapor in the stratosphere is going to increase the total amount of stratospheric humidity. And this is going to, in turn, decrease the temperature of the stratosphere because of all the radiative cooling is going to increase the temperature capacity of the stratosphere. And so it turns out that when you cool the stratosphere and inject a lot of aerosol and water vapor into the stratosphere, it decreases the amount of stratospheric ozone. And so the chemistry behind this was first formulated in 2001. So how can we study these chemical processes underlying the predicted decrease of stratospheric ozone as affected by climate change? So one way we can study these is through the study of large convective storms. So in 2017, there was a study showing that these very, very large convective storms over the central United States Great Plains actually produce enough convection to drive these humidified air masses into the stratosphere. And what this does is it actually activates these chlorine reservoir species that usually don't destroy ozone. It converts them into a form of chlorine that can destroy ozone very efficiently. And so this leads to ozone depletion in the stratosphere, and this was observed in that study. And so another way we can investigate the ozone depletion due to climate change is through explosive volcanic eruptions, such as the one I'm going to talk about later. And so kind of shifting gears, why should we care about mercury? And so mercury is a very potent neurotoxin, both in humans and in other mammals. And it bioaccumulates in marine ecosystems, meaning that lower in the food chain and smaller aquatic organisms such as shrimp and small fish, the concentration of mercury in the bodies of these organisms is going to be lower, but it's going to increase as you go up the food chain. So larger aquatic organisms such as like large fish and sharks will have much higher concentrations of mercury in their bodies. So most humans are exposed to mercury through three main routes: dental fillings, seafood consumption, and through various forms of occupational exposure. And the really important point to note here is that the largest source of mercury to bodies of water, such as the oceans and lakes where they can bioaccumulate, is from the atmosphere. So mercury in the atmosphere, present as a gas or in aerosol phase, will deposit to the surface of the earth. And so because mercury is very widespread in the atmosphere, the World Health Organization named mercury specifically on its list of 10 chemicals or groups of chemicals of public health concern in 2020. And so I'm going to give a very brief overview of the last 20 years of our understanding of atmospheric mercury chemistry. So mercury is primarily emitted to the atmosphere in what's referred to as gaseous elemental form, or Hg0 as shown here. So it's a vapor in elemental form. And once emitted to the atmosphere, like everything that gets emitted to the atmosphere, it undergoes oxidation. So eventually what happens is that as mercury becomes oxidized and enters this gaseous oxidized state, shown here as Hg2, it becomes more water soluble. And when it becomes more water soluble, it's much more likely to deposit out of the atmosphere and enter these aquatic ecosystems where it can cause human exposure and toxicity. And so for this reason, we care very much about how gaseous elemental mercury can be converted into oxidized mercury. And so very early models of mercury oxidation in the atmosphere relied primarily on oxidation by hydroxyl radical, or OH, shown here, and ozone. And these models actually produced results that were consistent with observations of both gaseous elemental mercury and oxidized mercury, but theoretical calculations showed that the chemical kinetics, or the speed of these reactions, was too slow to explain the observations. Get my mouse to cooperate here. Okay. So later models, because hydroxyl radical and ozone were ruled out, proposed that bromine atom was actually the primary oxidant of gaseous elemental mercury in the atmosphere. And these models turned out to be consistent with observations and theory. And so for quite a while, atmospheric chemists who studied mercury just assumed that bromine was the only oxidant of mercury that played a significant role. However, there's been a few studies in the last few years, starting in about 2020, that showed that it might be true that hydroxyl radical, which was first considered and then kind of disregarded, might actually play a more important role than previously thought. It might actually compete with bromine in the oxidation of gaseous elemental mercury. And so this comes from a few different points. So first, More chemical kinetic studies showed that this H1Br molecule that's formed by the reaction of elemental mercury with bromine actually photolyzes very quickly, meaning that the back reaction proceeds faster than previously thought. So bromine chemistry alone can't explain the amount of oxidized mercury that we observe. The second is that oxidized mercury measurements for the past few years have actually been discovered to be systematically underestimating the amount of mercury in the atmosphere because of analytical limitations. And so there needs to be more oxidation. A third point here is that the forward reaction of these short-lived Hg1 species, Hg1Br and Hg1OH, actually react very, very quickly with ozone. And this reaction is fast enough to outcompete photolysis. And so there's been some recent studies that show that kind of on a global scale, hydroxyl radical could be comparable to bromine in terms of how much mercury it's oxidizing in the atmosphere. And so this is kind of an overview of our current understanding of atmospheric mercury chemistry as implemented in a global chemical transport model, GeoSChem, which I'm going to show output from later. So mercury is emitted from a number of different sources, and the main source is anthropogenic or human-caused as gaseous elemental mercury, Hg0. And gaseous elemental mercury undergoes these fast reactions with bromine and hydroxyl radical to form these short-lived Hg1 species, which are highly unstable. And so these Hg1 species are quickly stabilized through reactions with ozone to form a longer-lived Hg2 species. And they're further stabilized through reactions with hydrocarbons such as methane, and they can form a very, very long-lived Hg2 species. And these Hg2 species, as I mentioned before, are highly water-soluble. And so they're more likely to enter the aqueous phase. And of course, once they enter the aqueous phase, they're much more likely to deposit out of the atmosphere and bioaccumulate in marine ecosystems and have implications for both environmental and human health. So the question that I'm asking is, since we're kind of reconsidering hydroxyl radical as an oxidant of gaseous elemental mercury on a global scale, should we reconsider also iodine? Because the role of iodine has been sort of largely discounted in the literature based on the fact that this Hg1I molecule here is too unstable, and two, there's not enough iodine in the troposphere to appreciably oxidize gaseous elemental mercury. And so I'm going to address both of these points later on. And so now going into some methods. So the primary measurement technique that I use in this work is multi-axis differential optical absorption spectroscopy, or MAXDOAS. And so it's a long word, but really what it means is we just put a telescope and we point it out into the atmosphere and we measure scattered sunlight. So it's not direct sunlight. We're not pointing the telescope directly at the sun, but just out in the atmosphere, all the scattered sunlight. And so in particular, we use our MAXDOAS instruments on top of these high altitude mountaintops. So the telescope will be placed on top of a mountain. And this gives us a couple of different kind of analytical advantages. The first is that our telescope is high above the planetary boundary layer, or the lowest level of the atmosphere. And the planetary boundary layer contains a lot of aerosols. And aerosols do two things. They shorten the observed measurement light path distribution, meaning that the amount of atmosphere that we're actually sampling will be shorter. And second, it makes it very difficult to interpret these measurements, the more aerosols there are, because there will be multiple scattering of this light, and the light path will be difficult to characterize. And so we're placing these telescopes kind of in the middle of the higher level of the atmosphere, the free troposphere, which kind of gives us a sense of the global background atmosphere. We also have sensitivity to the stratosphere, which is far above us here. And so when our telescope is pointed vertically or perpendicular to the horizon, we refer to that as a zenith geometry. When our telescope is pointed horizontally or parallel to the horizon, we refer to that as the limb geometry. And we also scan a number of different elevation angles. So the telescope will be moving and scanning different elevation angles between the zenith and limb geometry and below it. It's also useful for us to define what's referred to as the solar zenith angle, or SZA. And so a smaller solar zenith angle means that the sun is higher in the sky, and a larger solar zenith angle means that the sun is lower in the sky. So when the solar zenith angle equals 90 degrees, the sun is either setting or rising. And so these are the three mountaintop sites where we deployed MAXDOAS instruments. And so the first site is at Mauna Loa Observatory on Hawaii, which is in the kind of the tropical remote Pacific Ocean. And we measured there from February 2017 to present. The second observatory is in the southern hemisphere that I mentioned earlier, Maito Observatory. And we also measured there from February 2017 to present. And this is sort of east of Madagascar, between Mauritius and Madagascar. And the third observatory is Storm Peak Laboratory in central Colorado, about 3 hours north of here in Boulder. And so all of these observatories, as you can see, are at very high altitudes. So they're Storm Peak Laboratory and Hawaii are both above 3,000 meters, and Reunion is above 2,000. And so what does our data look like? Our very, very raw data looks like this. So each of these instruments has two spectrometers that measure ultraviolet visible scattered sunlight as a function of wavelength. And so we're measuring sunlight as a function of wavelength. And one spectrometer is turned more towards the ultraviolet region, and we measure from about 300 nanometers to about 460 nanometers. And the second spectrometer is turned more towards the visible region, and it measures from about 390 nanometers to about 560 nanometers. And so how do we use these spectra to measure these atmospheric trace gases that we're interested in? So atmospheric trace gases, some of them anyway, display characteristic fingerprint absorption patterns or structures that are shown here for ozone. And this is where we retrieve nitrogen dioxide. We can also measure halogen compounds such as bromine monoxide and iodine monoxide shown here, as well as small oxygenated volatile organic compounds, these small organic compounds such as formaldehyde on the left here and glycol on the right. We also measure what's referred to as oxygen collision-induced absorption, or O2O2. And so because the distribution of oxygen in the atmosphere is very, very well known, we can use our measurements of O2O2 to constrain our measurement light path distribution. So where are we actually measuring? Where is that light coming from? And so before I go on, I'm going to quickly define some terms here. So the quantity that we retrieve from these scattered sunlight solar spectra is referred to as the differential slant column density, or DSCD. And so what this is, it's the atmospheric trace gas concentration, but it's integrated along the measured light path distribution, and it's with respect to a reference spectrum that we use. So the measurements that we're making are relative to a reference spectrum. We also can define this reference slant column density, or SCD ref. And so this is the amount of trace gas absorption present in that reference spectrum that we're using. And most often our reference spectrum is a spectrum that we've selected for a geometry where we have the least amount of signal in our reference. And so on these mountaintop observatories, that's oftentimes kind of a midday zenith sky reference. And what we're trying to retrieve from our measurements is a vertical column density, or a trace gas vertical column density. And this is the atmospheric trace gas concentration that's integrated along the line perpendicular to the Earth's surface. And so this quantity is more directly comparable to other measurements, such as from satellite observations, as well as to chemical transport models. I'm also going to define the air mass factor, or AMF. And this is a unitless number which represents our measured light path distribution. And so it's basically the difference between our slant column and our vertical column. And so relating all these quantities, we can get this equation. So the vertical column density equals the sum of the DSCD plus the reference SCD divided by the air mass factor. Now I'm going to describe the long-term observations that we made. So this is what one day of measurements from one of these instruments looks like. So the top panel here shows our nitrogen dioxide trace gas DSCD as a function of time over the course of a single day. And the bottom panel here shows the ozone DSCD also as a function of time. And so the first thing you're going to notice is that these DSCDs change kind of dramatically with time during sunrise and sunset, that is during the early morning and late evening period. And that's because our light path is changing, our measured light path distribution is changing through the stratosphere. So the reason why we only point our telescope, and we point our telescope basically only vertically during the early morning and late evening, is because that's when we have the longest light path distribution through the stratosphere, and therefore a very, very high sensitivity to trace gases in the stratosphere. And so during, when the sun is higher in the sky and the solar zenith angle is smaller, that's when we're performing these elevation angle scans. And so we're actually moving our telescope and measuring these trace gas slant columns at different elevation angles in the atmosphere. And so what you see here is a time series of the nitrogen dioxide DSCD as a function of time, color coded by elevation angle. And so these elevation angle scans give us a very, very high sensitivity to the trace gas profile shape. And that's why there's a difference between the slant columns measured at different angles here. All right, so if we just take the zenith sky measurements at sunrise and sunset, so 2 data points per day, we can construct a very, very long-term time series of the total ozone column above each of our instruments. And so what we see here is the total ozone column at Mauna Loa Observatory in Hawaii as a function of time from early 2017 to present day. And there's some data gaps due to instruments maintenance and also due to a large volcanic eruption that occurred in late 2022, which cut power to the site, but the instrument is still there and we're going to get it running again. So the first thing you're going to notice is that there's this clear kind of seasonal periodic cycle in the ozone column over Mauna Loa Observatory. And so the hatched green here indicates the spring, the solid green indicates the summer, the hatched orange indicates the fall, and the white indicates the winter. And so there's kind of a maximum ozone column in late spring, early summer, and a minimum in winter. And this is primarily due to the fact that there's more sunlight during the kind of spring, summer period as opposed to the fall, winter period. And if you recall, ozone is primarily formed through the photolysis of diatomic oxygen when it's exposed to high energy solar radiation. And so if you look at our southern hemisphere sites, this is at Maida Observatory in Reunion Island near Madagascar, you see that the seasonal periodicity is switched because the northern hemisphere summer corresponds to the southern hemisphere winter and vice versa. But the time when the maximum and the minimums occur is the same in terms of the seasonality. So you also see a maximum in kind of the late spring, early summer, and a minimum during the late fall, early winter. And finally, at Storm Peak Laboratory, Colorado, where we sampled for a shorter period of time, you'll see that the ozone column shows a much, much larger magnitude of variability compared to the tropical marine sites. And that's primarily because of the overhead jet stream location changing a lot and therefore changing the observed maximum ozone. All right, so how do these measurements compare to a model? So what I did was I took a model from the European Center for Medium Range Weather Forecasts, or ECMWF, and they do this model called CAMS, or Copernicus Atmospheric Monitoring Service, and it's a global chemical transfer model. So it attempts to simulate atmospheric chemistry over the entire globe. And it's constrained by satellite observations. So it's not just a model simulation, but it's also constrained by satellite measurements. What you see here is the model output compared to our measurements. So the model is shown in purple and our measurements in blue. And you see that the model captures our measurements quite well, at least in a qualitative sense. And if we compare the model output to the measurements in a more quantitative sense using a correlation analysis, as shown here for each of the 3 sites, it does a decent job. It's not perfect, but it captures roughly both the magnitude and the seasonal variation of the ozone column at these 3 sites. And so just important to note here, the error bar on these measurements is on the order of 6%. And so within that 6% range, the model does a decent job most of the time, sometimes overestimates, sometimes underestimates. So we also did zenith sky measurements of the total stratospheric NO2 vertical column. And so what you see here is that compared to ozone, nitrogen dioxide shows a clear difference between sunrise and sunset, and this is primarily due to photochemistry. So at sunsets, the nitrogen dioxide column above us is much higher than the nitrogen dioxide column at sunrise. And the chemistry behind this looks like this. So during the day, nitrogen dioxide is exiting the form of N2O5 and NO3, and it's photolysing in the presence of all the sunlight, and it's forming more and more nitrogen dioxide. Whereas overnight, all this nitrogen dioxide is entering these different forms of reactive nitrogen, such as NO3 and N2O5. And so there's a really clear diurnal cycle. And the other thing I want to note here is that there's similarly a clear periodic seasonal cycle in the NO2 measurements. And this is for the same reason as for ozone. It's because there's more sun during kind of the late spring, early summer period, and there's less sun during the late fall, winter period. And so now we try to compare our nitrogen dioxide stratospheric vertical columns to the same model. And the model does a significantly worse job compared to ozone. And so you see that the model fails to capture both the magnitude and the variability of our measurements. And if we do a more quantitative comparison, it gives us the same message, which is that the model sort of systematically underestimates the amount of nitrogen dioxide we're seeing in the stratosphere. Now, this is also explainable in the sense that it turns out that this particular global chemical transport model does a pretty decent job simulating and explicitly simulating tropospheric chemistry, so lower atmospheric chemistry, but it doesn't explicitly simulate reactive nitrogen chemistry, the nitrogen chemistry that I showed in the previous slide. And so what I did was after seeing that it didn't really agree, I compared it to a different model, Geoschem, which I mentioned earlier, for a subset of the data. So this is just the total ozone and just the nitrogen dioxide column at Storm Peak Laboratory, Colorado. And if we compare it to this different 3D chemical transfer model that does explicitly represent reactive nitrogen chemistry in the stratosphere, it does a pretty decent job. So the slope here is almost perfect. It's very, very close to 1 in terms of the correlation, but there's outliers, and it's not perfect here, as you can see, but it does capture roughly the magnitude and the variability.
His defense. He's gonna be a doctor in like 20 minutes.
Let me mute the people here. All right, so our first case study is about reactive iodine and mercury at Storm Peak Laboratory, Colorado. And so just to refresh your memory, I was asking the question, can iodine appreciably oxidize gaseous element of mercury in the troposphere? And so first, to determine if iodine can actually oxidize mercury, we need to measure iodine. And so what we did was we measured iodine monoxide radical over the central continental United States at Storm Peak Laboratory for the month of April 2022. And so on the left-hand side, what you see here in this panel is basically a visual representation of the spectral absorption signal by that trace gas iodine monoxide. So on a low iodine monoxide day. And on the right-hand side, you see a map with the location of Storm Peak Laboratory indicated by this black star here. And these lines show where that air that we're observing this iodine monoxide in is coming from. So it's Lagrangian back trajectory modeling for 24 hours from high split stilts. So it simulates the movement of that air parcel that we're measuring back 24 hours. And you see that's coming from over the Pacific Ocean. And so each of these lines was initiated at a different altitude above Storm Peak Laboratory, and that's marked here. And for a day where we see a lot of iodine monoxide, the spectral absorption signal looks like this. And similarly, you see that the back trajectory modeling indicates that the air masses that we're observing this iodine in are coming from over the Pacific Ocean. Okay, so this is going to get a little bit technical for the next couple of slides. So I showed you how we retrieve total ozone and stratospheric nitrogen dioxide from just these zenith sky measurements towards sunrise and sunset. We haven't talked about the angle scans. So the elevation angle scans where we get all these trace gas profile information. So what we do is we take those trace gas DSCDs retrieved from these angle scan measurements of the solar spectrum, and we take a reference of our trace gas absorption present in our reference spectrum from some model output. And we also need to feed our retrieval an initial guess, which we refer to as an a priori profile, as well as an assumed uncertainty in that initial guess. And we also constrain our kind of measured air mass factor using a different model, which I also ran, called the radiative transfer model, which simulates the transport of radiation or sunlight through the atmosphere. So it's scaled to our measured oxygen collision induced absorption. So it's constrained by measurement. So we take all of these inputs, we can feed it into what's referred to as an optimal estimation algorithm. And it's a bunch of linear matrix operations that attempt to retrieve an optimal atmospheric state from our measurements and the initial guess, as well as the uncertainty. And from there, we can get at what we care about, which is these trace gas profiles and vertical columns. And so what I did was I performed a number of sensitivity tests, varying different parts of this retrieval algorithm to see how physically representative it was of our measurements. And so on the left-hand side here, you see the IO slant column density on the low IO day of April 6th, 2022. And on the right-hand side, you see the same quantity on the high IO day of April 16th, 2022. And so these are our measurements with an associated error. And so as for the initial guess that I'm feeding the retrieval, I tested two different profiles. So for the flat profile, we assume a constant IO volume mixture ratio throughout the entire atmosphere, just as a sensitivity test. And for what we think is a more physically realistic profile, we take output from this 3D chemical transfer model, GeoSchem, as an initial guess. And you see that the GeoSchem profile puts significantly more iodine monoxide higher in altitude above us. And so I said that we need to feed the retrieval algorithm a measure of our uncertainty in our initial guess. And so that's expressed here as the a priori error, which is given here as 10% as a first try. And I also, as an output from the algorithm, we get what's referred to as the degrees of freedom. So the degrees of freedom define, kind of describe the amount of independent pieces of information we're getting from the retrieval. And so like a single independent piece of information would be like a single column. Whereas as you increase the pieces of information, you're going to get more information on the trace gas profile shape. Okay, and so you see that both of these a priori profiles sort of underestimate the measurements on the high IO day, and the flat profile does a kind of a better job at 10%, but doesn't really capture the elevation angle scan. And so if we let the retrieval have more freedom in terms of how much it's going to vary from that initial guess profile, and we increase the a priori error to 25%, the agreement between the measurements and the forward modeled retrieved profile gets better. If we increase it more to 75%, it gets even better, and the degrees of freedom increases. At 125%, it gets better than before, 175%, and 300%. And so what I ended up doing was I actually went with the 175% case to propagate forward in our retrieval. But what you're going to see here is that two things. First, the flat a priori profile, if we use that as our initial guess for the retrieval, it doesn't do as good of a job at capturing the measured slant columns as the more physically representative GeoSchem profile. And so you see, like at this point and at this point, it's overestimating the measurements, whereas at these lower points, it's slightly underestimating the measurements. I'm just going to flash this up here, but these are the averaging kernels, which is another quantity we get from our retrieval, which is a description of where our information content from our measurements is coming from. And if we sum all of those averaging kernels, we get a column sensitivity, which is sort of a total sum of where information is coming from in the retrieval. And so because GeoSchem does a better job in terms of an initial guess for our atmospheric states than the flat profile, we can sort of qualitatively conclude from this that the IO volume mixture ratio appears to increase with altitude because the GeoSchem profile places more IO above us. And so I ran this retrieval for that entire month of April 2022 for a number of different trace gases. But the first thing I'm going to show you here is this time series of iodine monoxide vertical column in the troposphere. So below 12 kilometers, where our retrieval is most sensitive. And the measurements here are shown in red. And the model output from GeoSchem, which I'm comparing it to, are shown here in blue. And this second panel here shows the IO concentration in volume mixture ratio space at the altitude of the instrument. So whereas the top panel shows the column integrated above the instrument, this is the concentration at the instrument. And you see that the model sort of systematically underestimates the amount of iodine monoxide that we're actually measuring. And it turns out that at its greatest point, the amount of iodine monoxide we're measuring is actually up to 3 times larger than the model. And our instrument was placed alongside measurements of gaseous elemental mercury and gaseous oxidized mercury because we're trying to answer this question of whether iodine can actually oxidize mercury. And so what you see here at this panel is the measurements of gaseous elemental mercury in red compared to the model in blue. And what I want to point out is that the model does a decent job capturing at least the rough magnitude of the measurements. It obviously doesn't capture all the variability, but it's roughly accurate in terms of the order of magnitude. However, for gaseous oxidized mercury, as is consistent with previous studies, this isn't just this instrument. the model systematically underestimates the amount of gaseous oxidized mercury at the observatory, and actually up to an order of magnitude. So a factor of 10. So we also retrieved columns of water vapor in the troposphere, which I haven't really shown before, but it shows us that our retrieval is sort of physically representative. We are actually physically representing our measured light path distribution in the model, and so it's working. Because the model does a decent job in modeling water vapor transport through the atmosphere, and our measurements agree quite well with the model. We also retrieved nitrogen dioxide vertical columns in the troposphere, which doesn't agree as well with the model, but some past literature shows that these columns, that the model also struggles to represent some of the reactive nitrogen chemistry in the troposphere, as well as formaldehyde. But the key takeaways from this slide are that first, the model underestimates the tropospheric IO vertical column by up to a factor of 3, and the amount of gaseous oxidized mercury by an order of magnitude. So there's more iodine in the troposphere than was kind of previously expected. And there's a lot more gaseous oxidized mercury than was previously expected. So how can we sort of put these measurements towards answering our science question of does iodine oxidize gaseous elements of mercury? So what I used was what's referred to as a chemical box model. So it's a model that represents all of this gaseous mercury chemistry. And I ran that box model at a number of different altitudes, taking constraints from a combination of measurements and modeling. And so what you see here is a profile, vertical profile in altitude space of temperature in red and ozone in blue. And so the temperature is important because it controls the chemical kinetics or the rate of some of these reactions. And the ozone is important because of that fast ozone reaction of Hg1 species to form more stable Hg2 species. And so both of these profiles are taken directly from geoschem. And you see that this geoschem model output at least agrees quite well with our measurements of ozone at Storm Peak Laboratory, shown here as an orange dot. So we have a decent constraint on the ozone, at least at that altitude. And what I did was I took constraints on those molecules that we think are reacting with gaseous elemental mercury from the models and the measurements. So the bromine profile and the hydroxyl radical profile, as well as the chlorine profile, are all shown here in purple, yellow, and light blue, respectively. And so chlorine I included for sake of completeness, but it is actually kind of a negligible oxidant of mercury because of the amount. And it's scaled here by a factor of 10. And so bromine and hydroxyl radical are also taken directly from the model. But the iodine profile shape is taken from the model. But what I did was I scaled it using our measurements of iodine monoxide. So we're not directly measuring iodine atom, but it turns out that iodine atom and iodine monoxide radical quickly interconverts as a function of the ozone concentration. So if I take the ozone concentration, which we think is decently well constrained, I can actually scale our measurements of the IO vertical column in the troposphere to constrain the iodine atom concentration. And the iodine atom is what we think is actually oxidizing the mercury. And so this rightmost panel shows the vertical profile of gaseous oxidized mercury as a fraction of which molecule is contributing to the oxidation of mercury. So it runs from 0 to 1. And so 1 is that the molecule, is oxidizing all the mercury, and 0, it's not oxidizing any mercury. And so chlorine, again, I'm going to start with, it's scaled here by a factor of 10, and it's a negligible amount. So it wouldn't even be visible if I didn't multiply it by 10. Hydroxyl radical is quite important. It appears in the lower troposphere at this particular site using these model constraints. And bromine here in purple becomes a little more important above 4 kilometers and remains important up through the troposphere. And then I performed a series of sensitivity studies on the chemical kinetics of how important iodine is for oxidizing gaseous elemental mercury. So it turns out that the kinetics of iodine, because iodine has been disregarded for such a long time by sort of in the literature as an oxidant of mercury, the chemical kinetics are not very well constrained. So for the chemical kinetics of bromine, we have sort of direct experimental constraints of how fast it reacts with mercury. And for hydroxyl radical, we have theoretical constraints. Iodine, there's only like 2 papers that discuss these constraints, and they don't agree with each other. So what I did was I first assumed that the forward reaction of mercury with iodine, this Hg1 formation, iodine atom, is the same as the reaction of mercury with bromine. turns out that one of the papers, that there's evidence, at least theoretical evidence, that shows that it's probably faster. Mercury probably reacts with iodine forward faster than mercury reacts with bromine. However, similarly, the back reaction, meaning the dissociation of this Hg1 iodine molecule, is probably faster than hydroxyl radical, which is even faster than the dissociation of bromine. So what I did as a first guess was I took the dissociation rate constant of Hg1 hydroxyl radical and multiplied it by 100. And that's what you see here. And even in this very, very conservative estimate, which we think is a lower limit, iodine is actually competitive with bromine in the upper troposphere in terms of the oxidation rates of gaseous elemental mercury. And so it becomes even more important if I increase or decrease the rate at which HDI dissociates, which again is not very well constrained. And more important still, if we decrease it further. Now, if I take a rate constant reported in the literature for the forward reaction of HDI as faster than the forward reaction of Hg plus Br, then it becomes even more important. And if I perform a similar sensitivity study on the back reactions, then you see that there's a kind of a range of uncertainty where we can constrain the amount that iodine is reacting and oxidizing mercury. And so this shaded area indicates that range of uncertainty. But the big takeaway is that iodine is almost certainly pretty important for gaseous elemental mercury oxidation in the upper troposphere. But it might even be more important than bromine or hydroxyl radical, depending on how much iodine there is in the lower troposphere, depending on which kinetics you assume. So there's more work that needs to be done here. We need to perform more theoretical calculations at a higher level of theory and better constrain the chemical kinetics here using experiments. But the big take here is that iodine can rival bromine and hydroxyl radicals in oxidant of gaseous elemental mercury in the upper troposphere and perhaps even the lower troposphere. Okay, the conclusions from this part of the talk. These are the first ground-based observations of tropospheric iodine monoxide over the central continental United States. So past observations are primarily focused on marine and coastal sites because most of the iodine in the atmosphere comes from the surface of the ocean. Our measurements show that there is significant temporal variability over the continental United States. And the iodine that we observe is enhanced in these air masses that have been quickly transported from over the Pacific Ocean in less than 24 hours. Qualitatively, we can state that these iodine monoxide volumetrators increase with altitude. And the model underestimates the amount of tropospheric iodine by up to a factor of 3 and the oxidized mercury by an order of magnitude. So at these levels, iodine can rival bromine and hydroxyl radical as an oxidant of tropospheric mercury, particularly in the upper troposphere, but may be important in the lower troposphere as well. And this new oxidation pathway that is not currently included in any of these models, in geochem or any of these mercury chemistry models, can partially, but not fully explain the model underestimation of the amount of oxidized mercury in the atmosphere. All right, on to our last case study. So I had mentioned that we can use explosive volcanic eruptions to study climate change and its effect on stratospheric ozone. And so in January 2022, there was this massive underwater volcanic eruption in Hunga Tonga, which is kind of in kind of a remote marine area in the southern hemisphere. And it was larger than any atom bomb test conducted after World War II. And so this was the island of Hunga Tonga in December 2021, before the eruption. And this was the island after. And as a sense of scale, that's 3 kilometers. So this was an enormous, enormous explosion. So we published observations of this, of the volcanic plume from the eruption in this science paper, Rapid Ozone Depletion after Humidification of the Stratosphere by the Hunga Tonga eruption. But I want to call your attention to this map down here. So this yellow star here indicates the position of the eruption. And this yellow star here indicates Reunion Island, where our Max DOS instrument was measuring on Maido Observatory. And so the plume quickly traveled from Hunga Tonga all the way over Australia to overhead our observatory. And so the first big finding was that this volcanic eruption, similar to those mid-latitude convective storms over the Great Plains, injected a ton of water vapor into the stratosphere. And so it actually increased the amount of water vapor in the stratosphere by 10%. So the total amount globally was increased by 10%. And so a team of scientists that we that our collaborators launched a number of balloon radiosondes that measured the amount of water vapor, shown here in blue, as well as the aerosol backscatter. So the amount of aerosol generated from this water vapor is shown here in red and dark blue. And you see that they correspond to the same altitude ranges, meaning that all this water vapor is forming aerosol as it enters the stratosphere. And it's at a very high altitude. This is 25 kilometers above the surface. Also shown here is that all that water vapor cooled the stratosphere. And so the green here shows the vertical profile of temperature, also measured by the balloon sondes, as compared to this kind of predicted climatological temperature shown here in black with a gray uncertainty. And so these measurements were corroborated by measurements from a satellite, the NASA microwave limb sounder. This is, again, the position of Hunga Tonga, and this shows the transport of the plume into the stratosphere, as shown by the enhancement in water vapor volume mix ratio in the stratosphere. And all of this injection of water vapor into the stratosphere and subsequent radiative cooling resulted in stratospheric ozone depletion. So in the tropics, where you don't usually expect it. So the temperature is again shown here in green, and the temperature climatology shown here in black with a gray shading. And the anomaly of the temperature, meaning the expected temperature minus the actual observed temperature, shown here in this black line here. And so it's in Kelvin, but it's several kelvins below what was expected based on just the climatology. And so the ozone depletion is shown here in pink. So the ozone is shown in pink, and the climatology of the last 2 decades is shown as this dotted red line. And so it's significantly below what you would expect in the absence of the volcanic eruption. This was corroborated by measurements from the same satellite as shown here. So the blue indicates lower concentrations of ozone at 27 kilometers, and the pink indicates higher concentrations. You see there's an ozone depletion as the plume travels from the volcanic eruption to the observatory. All right, so our measurements constrain basically the role of the NOx cycle of ozone destruction, as well as the Brock cycle of ozone destruction. I'm only going to show the NOx here. But what I did was I took these Zenith-sky measurements of nitrogen dioxide radicals during kind of sunrise and sunset. And so that's what you see here. You see the sunrise period and the sunset period as a function of solar zenith angle. And this is just for January 2020. And that's sort of our baseline is January 2020. And so January 2021 you see that there's a decrease. We can actually explain this decrease. It's actually due to the injection of a massive amount of wildfire smoke from these Australian wildfires. And this is kind of well understood at this point, but it decreased the amount of nitrogen dioxide in the stratosphere. In January 2022, prior to the eruption, you see that after that reduction due to the wildfire smoke, it returns back to baseline. And so that's what you see here in red. And while the plume is passing over the observatory, you see that there's a significant reduction in NO2 in the stratosphere, as shown here by these black markers during the plume period. And if we kind of take the difference of all of these different traces throughout the years compared to sort of an interannual average, you see that it sort of emphasizes the fact that both January 2021 and the plume period both showed large reductions in stratospheric nitrogen dioxide as observed at this site. And so we also, we can explain this nitrogen dioxide reduction. So typically what happens, as I sort of described earlier, the N2O5 and NO3 will photolyze and form NO2 during the day. But if there's a ton of water vapor in the stratosphere, what ends up happening is it reacts with that water vapor to form nitric acid. And this nitric acid is highly water soluble and it enters the aerosol phase. And it's not going to come out for quite a while. And so we also made measurements of bromine monoxide radical, which I'm not going to show here, but basically it didn't really change. So there's not any evidence for enhanced bromine monoxide radicals. So the NOx cycle of ozone destruction and the Brock cycle of ozone destruction can't really explain the observed ozone depletion. So what can explain the observed ozone depletion is heterogeneous chlorine activation. So this top panel here shows the amount of HCl injected from the volcanic eruption. And it turns out there's not really evidence for any significant injection of this, chlorine into the stratosphere from the eruption. It's basically just as seen here. So that what's happening, we think is happening, is that the chlorine that's already in the stratosphere is being activated because of the stratospheric humidification and these cooler temperatures. And so you see that this reactive chlorine species, ClO, is significantly enhanced and where the plume passes through. And so there's not additional chlorine being injected into the stratosphere, but the chlorine that's already there is being activated into this form that can efficiently destroy ozone. And so the chemistry is shown here. And so what would happen under typical conditions is that this chlorine would be present as chlorine nitrate, HCl, HOCl, and Cl2. Turns out that when you introduce a lot of water vapor into the stratosphere, the additional water volume enhances all of these reactions. And so the production of Cl2 is enhanced, and this Cl2 will quickly photolyze to form Cl and ClO, which will very efficiently destroy ozone. And so in conclusion, a massive amount of water vapor was injected high into the stratosphere, which increased the amount of water vapor in the stratosphere by 10% globally. And this corresponded to a very large ozone depletion in the tropical stratosphere. And so this ozone depletion can be explained by heterogeneous chlorine chemistry, which was enhanced by the decreased temperature, the increased amount of water vapor resulting in more dilute aerosol, therefore increasing the amount of Cl2 production, and NOx decrease due to increased N2O5 hydrolysis. So turns out that I mentioned earlier that NOx can actually react with Cl and ClO to form chlorine nitrate, which is a kind of a long-term reservoir that can't destroy ozone. So the chlorine cycle of ozone destruction was enhanced by the decrease of NOx. There wasn't any apparent enhancement in BRO, but we think that the Brock cycle of ozone destruction was also enhanced because the Brock's and Clock cycles participate in a number of cross reactions that destroy ozone more efficiently. And this case study sort of simulates the effects of increased stratospheric water vapor due to climate change. All right, and that's all I've got. So I'd like to thank my advisor, Reiner, and all the friends and family who showed up here today, as well as my partner, Madison.
Body of work, congrats. Just curious, what are the implications for whether mercury is oxidized by the different species or pathways? Maybe all different the ocean. Does it affect distribution or what's?
Yeah, so
Can we check if online people heard
Yes.
this question?
yeah, did people online hear that question?
Yes, that one.
Okay, great. Yeah, so I think that kind of the main thing here is that I don't know if this answers your question, but we're seeing like way higher levels of oxidized mercury than we expect based on the current chemical understanding. And this is just like one additional oxidation pathway. So what we really need to do is do like actual simulations, like global model simulations, which implement this new chemistry. And that'll give us, I think, a better idea of where this mercury oxidation is occurring. So that the lifetime of atmospheric mercury is like on the order of months. So it is very globally distributed. And so this gaseous elemental mercury oxidizes very, very slowly. So I don't think that it's difficult for us to say, I guess, at this point, whether that mercury is going to be oxidized sort of, more over the oceans versus over the continents. And the other point is that this iodine that we're observing is in the free troposphere rather than in the marine boundary layer. And that's kind of where we're seeing the transport from. Does that answer your question?
So.
Yeah.
Great topic. I was curious with the eruption, you mentioned bromine. Is there anything interesting with iodine to look at there, or?
Yeah, so this was actually an expected question too, because we can measure iodine. So we didn't see anything really obvious in iodine, and we're really fighting right now. I mean, there's more work to be done here. Iodine is really hard to measure. I mean, we were on the low PPT levels. So it was actually a little unexpected that we saw this amount of iodine over the continent in the first place. And we don't really see like a large iodine signal when we're sensitive to the stratosphere, basically. And there's again, I think more work to be done here. So there's not really like low-hanging fruit. We're kind of limited by our analytical challenges in terms of actually measuring like iodine in the stratosphere right now. So I looked at it, but nothing obvious.
Madison first, Alex, then
So I just want to check, like, you're not measuring iodine directly, right? You can only measure the iodine monoxide. Is there any other forms that iodine takes in the atmosphere?
Yeah.
Like, if you're measuring, like, are there any ways to directly measure iodine? And is there any measurements being done, like, in the evaporator or two? So, there's your questions.
Yeah, I think, well, to answer the last question first, there are a lot of, so I think I might have said it, but most of these measurements of reactive iodine have been done kind of historically in kind of marine or coastal sites. So there's been a lot of ship-based and aircraft-based. Well, when I say a lot, there's been a handful of them, but the measurements that have been done have been focused on marine and coastal sites. And as in terms of measuring like other forms of iodine, I know that sort of this particular analytical technique can be applied to measuring OIO, which is another reactive form of iodine. There might be a couple of other species I'm not aware of, but and maybe Reiner knows, but I know that they do a lot of sampling of iodine from like directly measuring iodine atom and iodine ions in things like seawater. But beyond that, I'm not really familiar with a whole lot of other measurements of reactive iodine. The reactive iodine measurements that can be done are primarily through this technique that have been done sort of historically. I know that I think there might have been a paper talking about trying to do some of this in an infrared as opposed to the ultraviolet visible. And of course, you know, Jose measures iodine in aerosols. But beyond that, I don't know if that answers your questions.
Work in progress.
Yeah.
In reference to the Hunga Tonga eruption, I'm wondering if there was any like ash or smoke in the air that affected your measurements, because I know it relies on scattering, and how you dealt with that.
Yeah, so Hunga Tonga was like completely underwater. So there wasn't really an ejection of like ash or smoke. It was just, it is a massive explosion underwater, just injected a ton of water. Yeah, does that answer your question?
There was a question here in the front row, and then we go to Ted.
I was wondering if you had any kind of corresponding data from ocean measurements, and then if you see any delay or like the time frame from when you're seeing the ocean measurement of mercury or iodine or whatever, and then what you're seeing in the atmosphere.
Yeah, there are, I mean, not at the same. So our this particular, like, I guess, study was based at this mountaintop observatory. There are past measurements of people who measure like mercury in particular in a number of different kind of samples of water. There's someone, Peter Weiss-Penzias, he does measurements of like mercury in cloud and fog water, as well as in like animal carcasses. And there's a number, but mercury is pretty hard to measure because we're talking about like also on sort of equivalent PPT level, so parts per trillion level. So we didn't have any like corresponding measurements to what we were measuring at Storm Peak Laboratory in the ocean. But yeah, that's a short answer. But I guess the other point would be that mercury is like kind of transported globally because it's lasts in the atmosphere for months and months.
So there's a question online from Ted Dibble.
Yeah, so the question online says, regarding model underestimation of mercury 2, photolysis is a major sink for mercury 2, and the absorption spectra are mostly from one quantum chemistry study. Could the uncertainties in these results account for the underestimation? Honestly, I'm not familiar enough with the magnitude of the uncertainty in the quantum chemistry calculations to make a definitive statement. I think I'll leave it at that. The photolysis study that I'm familiar with that came out was Alfonso Saiz Lopez's paper in 2020, which is kind of where they were talking about how mercury bromide photolyzes faster than expected. But I'm not familiar enough with I think the details of the uncertainties there to really make a statement.
Follow up on that, or?
Not yet.
Ted, do you want to follow up on that?
Well, the 2017, hang on a second, get better audio here.
The 2017 Hannah Horowitz paper faced, well, in the process, they faced a problem that they were too much oxidation. And so they threw in a aerosol phase photosensitized reduction of mercury, which was way too high. And then that, when Cez Lopez paper came out, there was they showed that they had some experiments in showing much slower aqueous phase reduction, and they computed these very large rate constants for photolysis rate constants for reduction. And those methods are not really well constrained. There's and if you're off on the energy of the transition by 20 nanometers, and you shift something from 320 to 300 nanometers, you go from a appreciable photolysis rate to a very small one in the troposphere. So I think it's possible. It's also possible that those photolysis rate constants are underestimated, which would make the problem even worse.
All right. Well, thanks, Ted. I guess I was. Yeah, we don't know, right? Yeah.
Chris, really good talk. I was really interested when you were talking about the retrieval. You mentioned that you used the reference spectrum and also the a priori. For the reference spectrum, is there an uncertainty in that? I know you said that was coming from geochem.
Yeah.
Did you vary that in your sensitivity studies, or is that like significant as a source of error?
Yeah. So there's a couple of parts of that. The first is that I did simplify things when I said we took it from geochem. So what I do is I take a profile from geochem, and I constrain the reference slant column using basically our measured O2 SEDs, and then scale that to a radiative transfer model, because you can't just take the profile for geochem to calculate a measured slant column. You have to know your measured light path distribution. That's one part. And the second part is I did conduct sensitivity studies, which are not shown here. And I was able to get an error estimate. The amount of absorption in the reference spectrum is pretty small. And so it's not really a gigantic source of uncertainty. And then the sensitivity studies sort of constrain that.
That's our optimization, one should say, right?
Yeah.
That's highly using
Yeah.
Can you tell us how you chose the 3 sites for measuring?
So this is a kind of a long, because I didn't join Reiner's group until 2018. So I was kind of the person who took over these 2 sites after they had already been set up by other scientists. And so I didn't choose those 2 sites. I mean, they give us, from what I understand, and maybe Reiner can chime in on this, the initial interest in Mauna Loa Observatory and Maida Observatory was that we were studying the coupling of halogen radical species with these small oxygenated volatile organic compounds like formaldehyde and glyoxyl. And then Storm Peak Laboratory was sort of chosen primarily because, actually, I'm not actually sure that the rationale for choosing Storm Peak Laboratory, other than the fact that it was sort of one of our project partners is like the manager of Storm Peak Lab. I'm sure there's a scientific rationale, but
for one, we had mercury measurements.
yeah.
And, so that enabled clear thesis. Yeah, the northern hemisphere, southern hemisphere are just fundamental in the background science and also fundamental science interest to generate data in places where there's generally more data. And so satellites use those data as reference sectors and assume there's nothing going on there. And so Chris is showing that actually there's quite a bit going on there. And that has global implications for the satellite maps that he didn't really get into, but that was part of the motivation of choosing the northern hemisphere and southern hemisphere side. Sandeep?
Maybe this is related to the previous question. If mercury, if iodine is one of the unknown pathways that might be present or not, and if iodine is mostly present on top of seas rather than on top of the continent, do you see smaller uncertainty on top of your Colorado site for the mercury compounds, mercury 2?
So to clarify, are you asking if if the uncertainty in the mercury measurements is linked to the measurement site?
No, yeah, so the uncertainty, you don't know, how fast the mercury is reacting with iodine. If iodine was not present or present in very low concentration, then you would assume that the model that you have is perhaps okay. At least the iodine uncertainty is removed. And if there is a huge difference in iodine concentration above the ocean and above the continent, does that tell you something about how fast the iodine reaction is?
Yeah, okay, that I think I understand. So I think my response would be that it's very difficult to constrain where the oxidation is occurring because it's so long. It happens over the timescale of months. So unless you could track or model accurately an air parcel that contains, these oxidants and the mercury over the scale of months, it'd be very difficult to say exactly where it's happening.
So you said gaseous mercury is stable for months. Mercury 2 is also stable for months.
Mercury 2 is not stable for months. Mercury 2 is going to leave the atmosphere fairly quickly, but it's highly dependent on the washout, right? So unless you could say that, oh, there's a lot of precipitation or this amount of precipitation happening while after the oxidation has occurred and the transport is occurring, I think it'd be very difficult to say exactly where the washout is happening and where the oxidation is happening. Does that answer your question?
I have a question, I think on slide 25 or 26, when you're showing that IgG oxide, like daily cycles, it seems like it's like higher in the morning and the evening than in the middle of the day. I was kind of wondering why that was, or if that had to do with it.
Yeah. Yeah, let me go to that slide here.
And also that's like the measurements are just in the model.
Oh, you're talking about how there's this diurnal
Yeah.
cycle here. Put that on the big screen here and exit presenter mode. Yeah, I mean, that's in the measurements is this diurnal cycle. And so I don't know exactly, I don't have like a full recollection of where this diurnal cycle in iodine chemistry comes from. But iodine undergoes like a lot of kind of photolysis influenced, like light influenced processes. Like for example, like IO will photolyze back to form iodine atom. And I would suspect that it's entering some kind of reservoir species, overnight that we're not able to measure, but I don't have enough of a detailed chemical understanding of iodine in this particular context to say beyond that.
Okay. Last question from the audience. Go ahead.
During 6 years of research, you learned something, and what did you learn, and is it worth even in the future? Is it worth pursuing further in your research, what you have done?
Yeah, I think, what did I learn during my research? I mean, there's these conclusions of like, yeah, I didn't know anything about, I learned so much that there's too much to list, right? I learned about atmospheric chemistry sort of broadly. I learned about using these instruments, which I had very little experience with before. And in a scientific perspective, I learned that science is kind of hard in the field. You kind of go out there and you measure things. It doesn't always go as you expect. And there's always problems with instruments that need fixing. I think things that we could build on is this mercury chemistry is really unconstrained. I mean, Ted brought up this point. There's a very limited amount of studies that actually use measurements to constrain mercury chemical kinetics. And that could use a lot more work. Nobody wants to work with mercury because it's toxic, which is one of the reasons, and additionally, I think there can be better constraints on sort of, how, kind of calling back to the Hunga Tonga volcanic eruption, how climate change is going to affect stratospheric ozone in particular. There's a huge body of work of modeling studies that try to make estimates. but it's still pretty uncertain in terms of how much water vapor is going to enter the stratosphere and how much it's going to affect our ozone.
My question concerns the discrepancies of the measurements you've made with the model.
Yeah.
That fed back to the geochem people so they can fix it, or how does that work?
Yeah, the idea is that, well, this paper's in review now, so what the idea is it'll get published and then the modelers might look at it and say, actually, the co-author on this paper is one of the developers of a lot of this geochem chemistry. So the hope is that you would, try to implement some of the things here, but
Sometimes you need laboratory constraints to then pull it together.
It's a combination,
It's modeling bit.
combination of model development, laboratory measurements, and also probably the lower hanging fruit is quantum chemical calculations in order to advance our understanding of chemical kinetics as a starting point for these model developments. Let's say.
Good job, Chris. Congratulations.
thanks, Henning.
And, the audience